Hello there, I'm Mr. Math Guy, and today we're going to take a look at a 10-minute video on surface area of a regular polyhedron and a sphere. Before we get started, let's try to define or describe what a regular polyhedron is and what a sphere is. A sphere is pretty easy. A sphere, think of it as a ball of some sort. It's circular, it's a set of points equidistant from a given point, three-dimensional figure. Polyhedron is a three-dimensional shape, but a regular polyhedron is a polyhedron that all the faces are regular polygons. For example, an equilateral triangle or a square or a regular pentagon, and all of the faces, the same number of faces, intersect at each vertex. So maybe the best way to help you understand what a regular polyhedron is to show you some pictures. Now the interesting thing is there's only 5 regular polyhedra that even exist, that are only possible. So let's talk about all 5 of these, and then we'll figure out how to find the surface area of the polyhedra and a sphere. Now the other good thing about this is there's not a lateral surface area and a total surface area of a regular polyhedron and a sphere. It's just total. There is no lateral. There's not a base. So we are just talking about total surface area of a regular polyhedron and a sphere here. The first regular polyhedron that we're going to show you is called a regular tetrahedron. It's a tetra, meaning it has 4 faces. So if you want to kind of see the faces that we have here, we got this face right here, and it's a regular triangle or equilateral triangle. We would have this one, so here's number 2. You would have number 3 on the back side, back there, and then you'd have the 4th one, which is the bottom. So you got 4 faces, so it's a regular tetrahedron. Now, notice at each vertex, let's say this vertex right here, you have 3 different faces that intersect. 1, 2, 3. Or if you look at this vertex down there, you'd have this left front, the back one, and the bottom one. So there's 3 different faces that intersect at each vertex. The next regular polyhedron that we want to look at is called a regular hexahedron. We might just look at it and call this one a cube. So hexahedron is 6 faces. So cubes have 6 faces. Each face is a rectangle. And there would be a total, if you look at each vertex, you'd have the top, the left, and the front. So each vertex is intersected by 3 different faces. The next regular polyhedron that we have is called a regular octahedron. This kind of reminds me of maybe what a diamond or something looked like, although it's not. This one has 8 faces, and each face is an equilateral triangle. So there's 8 equilateral triangles, and at each vertex, let's say for this one right here, there's a total of 1, 2, 3, 4 faces that intersect at each vertex. The next regular polyhedron that we have is a regular dodecahedron. This polyhedron has 12 regular faces, and each face is a pentagon. And you can see at each vertex, if I draw here, we have 1, 2, 3. 3 faces intersect at each vertex. And the last regular polyhedron that we have is called a regular icosahedron. This particular regular polyhedron has 20 faces, and each face is made up of an equilateral triangle. And you can see that at each vertex, like this one, you have 1, 2, 3, 4, 5 faces that intersect. So if you were to take a look at this one, you have 1 face, 2 face, 3 face, 4 face, 5 faces. All of the vertices have the same number of faces that intersect. And these are the only 5 regular polyhedron that exist, that are possible. And that's a very interesting thing. And then lastly we have spheres. I think I can draw them somewhat. I couldn't draw the other ones very much, so I had to import some pictures. But a sphere, think about a sphere as, kind of like a basketball or some kind of a circular object. and all the points are equidistant from a given point. Now, if this were a basketball, for example, then this point that's in the center would be actually inside the ball. So you wouldn't be able to see the center of the sphere unless the ball were transparent. But it would be all the points equidistant from that given center point. So let's take a look at the two formulas that we will be learning here. The first one, the total surface area of a regular polyhedron. TA, total area, is equal to N, the number of faces that it has, times capital A, the area of one of the faces. So if you have a regular tetrahedron, which has 4 faces, each face is made up of an equilateral triangle. We'll just figure up the area of one of the equilateral triangles and then multiply that by 4, and that would be the total surface area of a regular polyhedron. Or if you had a cube, figure up the area of one of the squares, and then since a cube is a regular hexahedron, multiply that area by 6, and that would be the total surface area. Now, total surface area of a sphere, TA, total area, is equal to 4 pi r squared. So it's kind of like 4 circles all joined together. All right, so because the area of a circle is pi r squared, so total surface area is 4 pi r squared. Let's take a look at some of the examples. Let's say we have a sphere, and the sphere has a radius of 4. If we wanted to find the total surface area, we would say, well, TA is equal to 4 pi r squared. So our total surface area of this sphere, how much it would take to cover this area, would be 4 times pi times radius squared. And 4 squared is 16, and 16 times 4 is 64. So if you wanted to leave your answer in terms of pi, it'd be 64 pi square units. So we say we have another sphere. In this sphere, the radius is the square root of 5. Well, the formula is not going to change, so TA is equal to 4 pi r squared. And so TA is equal to 4 times pi times the radius, which is square root of 5, and squared. Now when you square a square root, it kind of just removes the square root. So it's just going to be 5. So it's 4 times 5, which is 20. So if you leave this in terms of pi, the total area here would be 20 pi square units. Let's take a look at the area of a regular polyhedron. This is a regular octahedron. It has 8 faces. Each face is made up of equilateral triangles. And let's say we know the area of one of these equilateral triangles is equal to 10 square inches. Well, the total surface area of a regular polyhedron is just N, the number of faces you have, times the area of one of them. Since we already know the area of one of them, and since we know this is an octahedron, it has 8 faces, times the area of one of those, which is 10 square inches, then our total surface area of this regular octahedron would just simply be 80 square inches. Let's take a look at the area of another regular polyhedron. This is a regular icosahedron, and this one gives us one of the edges to be 6 centimeters long. So we still use our formula. A is equal to N times capital A, and we know that this is an icosahedron, so this has 20 different faces. Now, the area, well, we don't know the area of this yet, but we do know that one edge is 6, and we do know that these are made up of equilateral triangles. So going back to our formula for equilateral triangle, we have A is equal to S squared times the square root of 3 all over 4. And since we know one of the sides is 6, 6 squared is 36 times the square root of 3 all over 4. And you can reduce there, and so you get 9 square root of 3. So the area of one of these is 9 square root of 3. And since you have 20 of them, 20 times 9 square root of 3 is 180 square root of 3 squared centimeters. And so this would be the area of a regular icosahedron with an edge of 6 centimeters. Just a quick review here. This is a regular dodecahedron. And how many faces did we say a dodecahedron had? Well, it has 12 faces. Now, how many edges does a dodecahedron have? Well, if you were to count all of these edges around this whole thing, you would get a total of 30. And if you counted all the vertices, you'd have a total of 20. Thank you for watching. God bless.